In this class, we will be talking about the notion of propositions. Okay, so what is a proposition? A proposition is a sentence that's either true or false. Okay, but not both. Okay, so for example, if I talk about, let's say, 2 plus 3 equal 4, this is a proposition, and this happened to be a false proposition. If I talk about, 2 times 4 equals 8, this is a proposition whose value is true, right? If I state the statement, it is raining today, this is a proposition that is true or false. Is it raining now? If it's raining, then this is true. If it's not raining, it's false. However, if I look at 2 plus 3, this is not a proposition. This is not a statement that I can assign to it true or false. Another example, if I say x greater than 15, this is not a proposition because I don't know if this is true or false. It depends on the value of x, and x is unknown, right? If I go and say, for example, study well, this is not a proposition. This is not a statement that I can assign to it true or false. Okay, so a proposition is a statement that is either true or false, not both. And we usually, to denote propositions in the abstract, when we are talking about abstract propositions, we use symbols like P, Q, R, and S. This is just a convention. It doesn't make it wrong if we call a proposition X or Y, but just as a matter of convention, we use P, Q, R, and S. So for example, this statement of 2 plus 3 is 4, I can say this is the proposition P, 2 times 4 equals 8. This is proposition Q, and it is raining today. For example, I can say this is proposition R. Okay, so this is just a matter of naming. Now, we have these basic propositions or atomic propositions P, Q, R, and S, but we cannot have every statement we want to make in math based made in terms of these basic propositions. We usually want to make more complex ones. So for example, I want to say, in a computer program, I say, if x greater than 5 and y smaller than 19, then something. Okay, x greater than 5 and y smaller than 19 for specific values x and y. This is now start to become a compound proposition where I have two propositions, x greater than 5 and the other proposition y smaller than 19, and I created a compound proposition from them using and. Okay, so I took what we call conjunction of these two. So if you give me basic propositions P and Q, then I can build another proposition which is the negation of P, not P. And I can also say P and Q is a proposition. This is the conjunction, or P or Q, then that's also another conjunction. So for example, I can say 2 plus 3 equal 5 and 7 times 10 equal 100. Okay, so this is a compound proposition because this 2 plus 3 equal 5. This is proposition P. 7 times 10 equal 100 is Q. So I have really a compound proposition P and Q. Of course, this one here turns out to be false because we know that P and Q, in general, when we talk about it in English, when I say something and something else, for this to be true, both of them have to be true. Okay, and this takes us to the notion of truth value. So the truth value of a proposition is that it's either true or false. So it's really about, if you look at a proposition, it has to evaluate to one of two values, either true or false. Okay, and one way to establish the truth value of a proposition is using the notion of a truth table. Okay, the truth table, basically, it's a table where we create a row for every possible combination of true and false values for the basic propositions, and then we evaluate the compound proposition for that combination. Okay, so for example, if I want to show the truth table for the negation of P, the way to do this is by saying, let's create a row for every possible combination of true and false values for the proposition P. And if you think about it, there are two possible assignments of truth and value to P. It's either true or false, okay? And the truth value of negation of P is that when P is true, negation of P is false. And when P is false, the negation of P is true. So this what I just wrote here is the truth table of the negation. Similarly, if I want to do P and Q, now if I look at every combination of true and false for P and Q, and then I need to evaluate P and Q, now we have more combinations. Both of them could be true. T true and P is false, or P is false and Q is true, or P is false and Q is false. And now we have to evaluate this and say, what is the truth value of P and Q? Well, if both of them are true, then P and Q is true. Otherwise, P and Q is false. So if at least one of these two propositions, P and Q is false, P and Q evaluates to false. Similarly, we do P or Q. So we can write every possible combination of P and Q, and we have true, 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 false, false, true, and false, false. And the interpretation or the semantics of this disjunction in logic is that if at least one of P and Q is true, then P or Q is true. So this will be true here, this is true, and this is false. This disjunction, P or Q, is actually worth commenting on, because when we talk about or in natural languages, like in English, for example, so when we say to someone, either study or, go play football, for example, then we usually mean by that the exclusive or. Do one of the two but not both at the same time. Now what we have here is really an inclusive or. So either if one of them is true, then P or Q is true. If both of them are true, P or Q is true. Okay, so this is what we call inclusive or. Now we can of course think about more than these. So we have the negation, conjunction, disjunction, but then we can start building more and more cases. So for example, here on the left hand side, we have what we call the exclusive or, P exclusive or Q. And this is unlike the inclusive or. This evaluates to true only if exactly one of these two propositions evaluates to true. So I can now say P, Q, and P exclusive or Q. And again, they can be all four possible combinations. And the P or Q is true if exactly one of them is true. So this will be true here, and it will be true here. But if both of them are false, it is false. If both of them are true, it is false as well. Okay? Another important, so this is here again, this is the exclusive or. Another very important operation that we deal with in logic is usually what we call the implication. So this is the if statement. So for example, when we say P implies Q, this is saying if P, then Q, okay? If you study, you will pass the test. P implies Q, or study implies if you study, implies you pass the test. So what is the truth value of this? Again, we have all four possible combinations. So this could be true, 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 false, false, true, and false, false. Now, it's very important to pay attention to this here. So P implies Q is true in all cases except when P is true and Q is false. So let's start actually when P is false. One of the general statements we always make is that if the premise is false, then the statement is always true. So if P is false, P implies Q is true no matter what Q is, okay? But if P is true and Q is true, this is as well true. This is the only case where it is false. So if the premise is true and the conclusion is false, then the entire statement is false, okay? And this is the truth table of P implies Q. The last one here on this slide is the bidirectional implications, or what sometimes you see it mentioned in the context of if and only if, okay? Or sometimes we write it IFF, in mathematical theorems. So this says that P is true if and only if Q is true, or P is false if and only if Q is false. So this P bidirectional implication Q is true in the two cases where either P and Q are both true or P and Q are both false. Okay, so if we look at this, we have the following case here. It's true, 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 false, false, true, and false, false. So if both of them are true, this is true. If both of them are false, this is true. And if one of them is true and the other is false, this is false. Okay. Now, one important thing to think about, or one interesting thing to think about, is look at the connection of these two, the exclusive OR and the if and only if, right? So you'll see that they are actually the complement of each other. The exclusive OR is true when exactly one of them is true and the other one is false. P if and only if Q is true if both are true or both are false. So they are really complementary to each other. Okay? And of course, we can start building more and more compound proposition using all of these here. So if I want to do P or not Q implies P or Q, the way to do it is actually to take it one step at a time rather than have just three columns, one for P, one for Q, and one for the entire proposition. So the right thing to do here is to write P and then one column for Q, and we should have one column for P or not Q, and we should have one column for P and Q, and we should then have one column for P or not Q implies P and Q, which is really our column of interest here. And then we build this, and we have four possibilities still: true, 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 false, false, true, and false, false. Okay? So if both of them are true, since P is true, this is true, and this is true. And if P is false and Q is true, this evaluates to false now, because not Q is false, P is false, false or false is false, and the other one is true. P and Q, this is just the and, we have seen it before. This is true, false, false, false. So now what we have here on the right hand side is the P or not Q. So if I call this, for example, here, if I call this R and this is S, this is column R and this is column S, and now I just need to look at the truth table of R implies S. Okay, so true, the first row here, true, true, we know that this implication is true. True implies false is false. If R is true and S is false, R implies true, R implies S is false. False, false is true. True, false is false. Okay, so this is how we would build the truth table for these kind of propositions. And you can keep building, and you can have a proposition with P, Q, R, and S, and you just keep adding more rows to the table. Okay. Now, if we have a compound proposition that no matter what truth value you assign to the basic propositions in it, that compound proposition evaluates always to true, we call this a tautology. So look, for example, here at these examples, P or not P. If you build the truth table for P or not P, you will see that if I build it for P or not P, so this is P, and this is not P, and P or not P, you will see that the rightmost column will have only true values. True, okay? So if this is true, and this is false. So not P will be false, and this will be true. So P or not P, true or false is true, and here false or true is true. So if you look at this column, it's all T. It's all true. This is why it is a tautology. No matter what value we assign to P, it is always true. Same thing with P implies Q or not Q. If you build the truth table, you will see that that column for this proposition will be all true. The last one is the most trivial of them. If you take true or anything, it's all, the value of that proposition is true. Okay? So a tautology is a proposition, a compound proposition that always evaluates to true. On the other extreme, we have the notion of contradiction. Contradiction is a compound statement that always evaluates to false. So if you look at P and not P, if P is true, not P is false, P and not P is false. If P is false, not P is true, P and not P is false. So this proposition always evaluates to false no matter what P is. The same thing with if and P. So if you take the conjunction of a false proposition and any other proposition, the resulting proposition is false. And this is a contradiction. Okay? And the last one is something in between. That's not always true, not always necessarily false. But we talk about the notion of satisfiability. So if you have a compound proposition, it is satisfiable if it evaluates to true under at least one of the truth assumption, the truth assignments. So again, if you take, for example, P or Q is satisfiable because, for example, if you set P to true and Q to false, this evaluates to true. So P or Q is satisfiable. Okay. Notice that if a compound proposition is a tautology, then for sure it is satisfiable. Okay. But if it is a contradiction, then it is not satisfiable. Okay. So it's very important to distinguish between these two cases. If a proposition is a contradiction, then it is not satisfiable. If it is satisfiable, it is not a contradiction. The same doesn't hold for tautology. If the statement is a tautology, it is satisfiable. But if the proposition is satisfiable, that doesn't necessarily mean it is a tautology. Again, P or Q is a satisfiable proposition, but again, if I write it here, P or Q is satisfiable, but not a tautology. Okay? And I will end just with a couple of words about this notion of satisfiability because this is a central problem in computer science. So then the problem of checking whether a proposition is satisfiable or not is known the propositional satisfiability problem, okay, or SAT, known as SAT. And it is defined as follows. So the input is really just a compound proposition. Someone gives you a compound proposition and they are asking you, is it satisfiable or not satisfiable? It's that simple question. Now, how would you go about answering that question? Of course, the most trivial way of answering this question is by saying, let me build the truth table for it. Well, suppose you have 1,000 basic propositions in that compound proposition. So imagine that you have P, Q, R, S, T, U, and so on. You have thousands of those. What's the number of rows in the truth table? If you do the math, you will find that the number of rows in that truth table is 2 to the 1,000. So just to build that table and to go through 2 to the 1,000 rows to see if one of the rows evaluates to true, you will see that that's not a feasible algorithm to run in practice. Okay? And the question then, can we do better than that? Is there another algorithm? Is there a better way than just inspecting 2 to the 1,000 rows or 2 to the million rows if I have million basic propositions? The answer to that, unfortunately, is that after so many decades of trying, nobody has been able to come up with an algorithm that always works and substantially better than basically trying every possible combination and every possible row in the truth table. And this central problem in computer science actually earned two famous computer scientists the Turing Award, which is the biggest award in computer science, to two computer scientists, Stephen Cook and Richard Karp, for the SAT problem. In fact, Stephen Cook showed that this problem is what we call npcomplete, which basically means that we do not know at this point. These two results combined by Stephen Cook and Richard Karp mean that so far we do not know of any feasible algorithm for this problem. I'm not going to be talking about this more formally than this, but if you are curious about this, you can basically search on the web what is SAT, what is npcomplete. You will find that until today we do not know of an efficient algorithm that can run in running time, that can take running time substantially better than let's try to build the entire truth table of the compound proposition.